everyone. This is the final video in this series. We're talking about convex mirrors. So please again review the previous material we did, especially the intro video on sign convention and notation. Also, we went ahead and analyzed the image of an object produced by a convex mirror. And we did another video on exercises already. So this is the last video. So let's go ahead and begin. All right. So we have an object that produces a virtual image 40 centimeters away from it. If the object is 40 centimeters away from the convex mirror, what is the focal length of that mirror? What is the magnification? So remember, for a convex mirror, if this is the object, the image has to be here. So this is DI, this is DO. All right, so we're given that the distance between them is 48. This is 40, so this has to be 8. Yeah, the object is 40 away from the convex mirror. The distance between them is 48, so that's got to be 8. So let's write what we have right now. D sub O is 40 centimeters. D sub I is negative 8 centimeters. Again, this is a convex mirror. What's the focal length? So 1 over F is 1 over DO plus 1 over DI. So 1 over F is again DI plus DO, DI times DO. Now flip those. All right. Now what do we do? Plug them in. So F 40, negative 8, 40 plus negative 8. So 40 plus negative 8 in the denominator, this is like 40 minus 8, or 32. And on top, we have 40, and then we have negative 8. So we can divide things. Divide by 8. So first of all, there's a minus out here from this. 8 and 32 will leave me with a 4 here, and the 4 and the 40 will leave me with a 10 up here. The focal length is negative 10 centimeters. The radius is 20 centimeters. Okay, negative. Great. So this is the focal length. Now we can look at the magnification. Negative DI over DO. DI is negative 8. DO is 40. So we have here, minuses cancel, 8 over 40, or 1 over 5, 0.2, 20%. Okay? So let's see what we have from ray tracing. So here, again, I started with a focal length of 10 and a DO of 40. Let's make sure the image lands at 8. Okay? So there it is. Parallel, reflected as if it came from the focal point to the mirror, reflects on itself, and then through the focal point, bounces back parallel. They all meet over here, somewhere, roughly over here. Each unit is 4, so that's at 8. And it looks like this is a little bit below a half. This is 2, right? If H sub I H sub O is 2. H sub O is M times H sub I. The magnification was 0.2 times 2, 0.4. So a little bit less than a half centimeters. There it is. Great. Next exercise. So we have an object that's 4 centimeters tall. So H sub O is 4 centimeters. 16 centimeters from a convex mirror. So D sub O, 16 centimeters. Produces a virtual image that is 1 centimeter tall. So H sub I is 1 centimeter. It's not -1, it's 1 because it's a virtual image, it's upright, so anything pointing up is going to be positive. What's F and where is D sub I? Right? So we know that from the magnification, which is negative D sub I over D sub O, which A sub I over H sub O, we can work with these two and get D sub I right away. So we have negative D sub I over D sub O is H sub I over H sub O. Cross multiply, I'll just bring the DO over and then the minus sign. So it'll be D, there's the negative DO HI over HO. So D sub I equals negative D sub O. So here's the negative D sub O. D sub O is 16. H sub I is 1. H sub O is 4. So this is negative 4 centimeters. So D sub I is 4 centimeters to the right of the image, the lens. Sorry, mirror. Lens is mirrors, images. So it's 4 units to the right of the convex mirror. So now what is the focal length? So again, use the original equation that we start with. And again, if you follow through this series, you will know that this is what the focal length will look like after we combine these and we flip. So we plug numbers in. DO is 16. D sub I is negative 4. D sub O also 16 plus minus 4, plus negative 4. All right, so F equals 16 times negative 4 over 16 minus 4, or 12. So 16 times negative 4 over 12. The 4 and the 12 will give me a 3 here. So it's 16 over 3 with a minus. This is roughly, 5.333 with a negative. Okay, and then the 3 keeps repeating. Okay. So let's see again now if all this is confirmed by ray tracing. So here's my object, the 16 centimeter mark. Each unit is 4. Let me see. 1, 2, 3, 4, 5, 6, 7, 8, 2. And I put the focal length as 5.3. So here's 1, 2, that's 4, that's 6. It's closer right here. And let's see where the image lands. So again, the first ray, parallel, bounces out as if it came from the focal point. Perpendicular to the mirror, meaning going through the center, bounces back on itself, through the focal point, interrupted by the mirror. That's again to show you that I was going through the focal point, comes out parallel, and they all meet over here. there's the image. The image is 1 unit long, again, 1 centimeters. It's at 128 centimeters away. It confirms the algebra exactly. All right. All right, folks, this is the last problem. So we have an object that's 30 centimeters away from its virtual image. So here's the lens. Here's DO. And the image here, the distance to the image is DI. Now remember, the I is less than 0. So we cannot write, let's think about it. The distance between them is 30. So if DO is 10 and DI is negative 20, how would we get the 30? We'll say 10 minus negative 20 will give me the 30, distance between them, right? So basically, again, because DI is going to come out negative, then DO minus DI is 30. But also we know that the magnification, it is 4 times as large. So the magnification is a quarter. That means the object is 4 times as large as the image. So this is going to be the negative DI over DO. Okay. The magnification is positive because this is a virtual image and it's upright. Okay. So now DO is negative 4 DI. Let's plug this in here. For DO, negative 4 DI minus DI is 30. Negative 5 DI is 30. DI is negative 6 centimeters. And from that, right away, we plug in here. DO is negative 4 times DI. Negative 4 times negative 6, 24 centimeters. So now let's compute the focal length. And we start with this. And with algebra, we get to this. DI. Negative 6. DO. 24. DI plus DO. So it's 24 minus 6. So let's see what we have. That's 18. Negative 6 times 24. The 6 and the 18 will cancel, will give me a 3 in the denominator. Now we'll have a negative 24 over 3, negative 8 centimeters. The focal length is 8 centimeters. The I is 6, which is inside the focal length. That's good. It's closer to the image, to the mirror than the object. The object is at 24. So let's go ahead and test it out. Starting with an object at 24, focal length at 8. So each unit is 2. 1, 2, 3, 4. Here's the focal point. And this is 12 units to put me at 4 centimeter object. Parallel ray bounces off as if it came from the focal length, a focal point. Perpendicular, meaning going through the center, interrupted, bounces back. And again, I'm showing you that it would have gone through the center if it wasn't for the mirror. And a one going through the focal point gets interrupted, bounces back parallel, and we trace them back over here, and the object sits at 3 units away, 1, 2, 3, which is 6 centimeters, which is exactly what we got before. All right, and that's all, guys. Thank you very much for following us in this series. The next topic in optics, we will be doing compound optical elements, where we have mirrors and lenses together. So you could have a converging lens with a diverging lens. When you look at the final image, and here's the object. Or you could have a converging lens and this type of mirror, or converging lens, and this type of mirror, convex mirror. And you just put an object here and see where the object, what the image is produced by this combination of compound optical elements. And I don't think we're going to go beyond 2 elements, maybe 3, but I think we'll stick with 2. It gets too complicated with ray optics, but we could do, using the thin lens equation. It doesn't matter how many elements we got. Okay, so if we do 3, it will be more algebraic using the thin lens equation. If we want to do ray tracing, we'll stick with 2. All right. So again, thank you. Like, comment, subscribe, and we hope to see you in the next series on our channel. Goodbye.